Hello class, this is the video for assignment of IV infusion. You'll in the assignment you will see this table, first table where it is asking you to calculate. First thing, it is asking you to calculate steady state concentration. To calculate steady state concentration, one approach would be you just plot this data. Here these are the data. You plot this data and you see the profile. Insert. Here. You see, based on this profile, you can say, well, this some student may get confused. Oh, this could be the steady state concentration, or this one, or that one. To avoid this confusion, what you do, you divide each concentration by the previous concentration. As you say, assume steady state if the concentration is equal to or greater than 90% of the previous concentration. So always you have to remember this when you are calculating. So to do that, you first take, for example, 0.767 divided by 1.46. I guess you'll get here 0.767 divided by 1.46 multiplied by 100. You see, it's 52%. So if you go back, so this is 52%, the difference between them. So similarly, you can calculate the percent difference between 146 divided by 195. It would be something like, let me check my cheat sheet, 75%. The other one, 1.95 divided by 2.04 would be about 96%. And then the last one, 2.04 divided by 2.14 is going to be 95%. So as you see, the differences between these three is more than or equal to 90%. So in that case, you take average of this. You take average of this and you consider this is as your CSS. So to calculate average, everybody knows how to calculate average. So you go to your calculator, add 1.95 plus 2.04 plus 2.14 divided by 3, which is 2.3. So your CSS here, in this case, your CSS is going to be 2.04. Now to calculate elimination rate constant, as you see, you have multiple sample before CSS and after CSS. So when you have multiple sample before and after CSS, what we do, we calculate CSS. We calculate CSS minus C, and then we will take natural log of this and plot against T. So here I have done the calculation for you. I have done the calculation. Oh, sorry for the problem. So here this CSS, if you look into this is your CSS, and you subtract first from, sorry, stop blinking. Here you subtract from 0, and then you can subtract from 0.76 and 1.76. so this would be CSS minus C, each time 2.04 minus 0, 2.04 minus 0.76, 7, 2.04 minus 1.46. So here you have CSS minus C, and then you plot. You should get a plot like this, and that slope of this would be 0.314. So this would be UK. So UK is, so here in this case UK is going to be 3.14 per hour. So to calculate K, you have the A now. K. Now you are going to calculate T half. T half is equal to 0.693 divided by K. K is 0.314. This should give you a value of, I think, is 2.21 hour. So this you have your K, you have your T half. Let's now clean this. So we are going to now calculate clearance. In case of clearance, we have to use that equation. If you remember, this equation is CSS is equal to R by CL. R by CL. So let's remove this. So here we have an R. R is equal to this one, 0.68 milligram per hour per kilo. So and the patient has a weight of 111. So you have to calculate R is equal to 0.68 multiplied by 111. I think it is something like 75.48. So this is R, and this is 75.448 milligram per hour. Let's clean this. It is 48 milligram per hour. My 4 is always bad. So and then you have a CSS of what? CSS is 2.04 milligram per liter. If you carefully look into the problem, the question it is asking, it is asking for CL clearance in milliliter per minute. So first you calculate CL. CL would be R divided by CSS. So your R is 75.48 divided by CSS is 2.04, and this will come as, I think it would be 37 liter per hour. So and then you can multiply this 37. You know that perhaps you know that 1 liter per hour is equal to, I think it is 16.67 milliliter per minute. So if you multiply this 37 times 16.67, let's go to my fancy calculator. So 37 multiplied by 16.67, it gives you 617. So your CL here would be 617 milliliter per minute. You have to always look into the unit, otherwise you will get confused. Now volume distribution. In case of volume distribution, we have to use an equation. If you remember, that equation is what? In case of volume distribution, we will use an equation. V is equal to CL by K, and we have previously calculated CL in liter per hour is 37. So let's clean this up. So we now know that, let's clean this, we have to calculate volume distribution. So we know that CL is 37 liter per hour. K we know is what? 0.314 per hour. So we put 37 divided by 0.314. 37 divided by 314 is to 37 divided by 0.314. It is 117. So there you go, 117, or you can say it is 118 liter. So this is asking for volume, the volume distribution in liter. So your volume distribution is 118 liter. If a bolus dose, if the goal had been immediate achievement of steady state at the start of infusion, for bolus dose we have to use this equation. I think I showed you this equation. This is the equation. So it is dose is equal to steady state concentration times volume distribution. So this is bolus dose. Bolus dose is equal to CSS times CSM times volume distribution. Volume distribution is V. So what we have CSS, we know 2.04 milligram per liter, and V is, we have 118 liter. So if you multiply this 2.04, let's go back to 2.04 multiplied by our volume of distribution is, I guess, 118 would be 242. So 242, or you can use also say that it is 241. So your bolus dose would be your bolus dose would be 241. So let's clean this up again. So we are done with this part. So the most important thing for you to remember that this conversion, and also you have to change this to the patient weight, because this information is given in per kilo. The next thing you have to do, again, you have to calculate elimination rate constant. To calculate elimination rate constant, in this case, you see you have two samples which are drawn after infusion has been stopped. These are two data. So we have two data, which is 4.5 hour. We have 0.505 milligram per milliliter. At 9.5 hour, we have 0.102 milligram per milliliter, and the last time point for infusion was, which is 0. This is 0 is equal to 2.114 milligram per milliliter. So you plot this data. There you go. So go here. So this data, you plot 0, 4.5 and 9.5, and you will get a slope of this, and this would be your K, new K. So K would be, your new K is equal to, your new K is going to be 0.32. Let's see if it is correct. Yes, your new K is 0.32, and based on this new K also you can calculate a plasma half-life. T half is equal to 0.693 divided by 0.32. It would be, plasma half-life would be, I think it's 2.17. 2.17. So this is how you calculate K for post infusion data. Okay, now the last few questions. The lack of response was attributed to because of low CSS. So then the physician or pharmacist suggested to increase the CSS to 5.8 milligram per liter. Assume if there is no drug left in the body, new infusion you start. So then calculate new infusion rate. So again, always we have to remember this equation. It's a very important equation. CSS is R over CL. So they are asking us to calculate R. So to calculate R is equal to CSS multiplied by CL, and your new CSS is 5.8 milligram per milliliter, and CL, if you remember, it is 37 liter per hour. So 37 liter per hour. So your R would be 5.8 milligram per milliliter here. The new let's look at my numbers. So new R is 5.8, and then you multiply with 37. So your new infusion rate would be 214, 250. So your new infusion rate would be 250. R is equal to 250. So now the time to reach steady state concentration, and then it says use post infusion data. So we know T half for post infusion, T half for post infusion we found is 2.17. Here, this is the post infusion data. T half was 2.17 hour. So as we know, time to reach is 3.3 half-life. So you multiply 3.3 times 2.17, it should be 7.16. Let's go back here. It's correct. 3.3, 2.17. So 3.3 times 2.17. It is 7.16. There we go. Time to reach would be 7.16 hour, and this is called time to reach steady state concentration. A bolus dose to achieve the new steady state immediately. So here in this case you have to use again that equation for bolus dose. We go back this one, dose is equal to V times C0. So if you look carefully here, a bolus dose is equal to V times CSS. So we know what was the volume distribution. Volume distribution was, I think, our volume of distribution was 118, and CSS, as he mentioned, is use infusion data. So it would be 2.04, 1.4. 118 times 2.04 would be 200. Let's see, this may be not correct. Volume of a bolus dose in milligram. The bolus dose in milligram is bolus dose is equal to, what was the volume of distribution in liter? Let me find the volume distribution in liter is 118 times 2.4 CSS. Please let's do touch of the statistic immediately. And bolus dose to steady. Just a minute. I'll skip this. I'll make this correction later. And then steady state concentration. Steady state concentration. If we increase the infusion rate, it R to 280 milligram per hour, then and then you have to calculate CSS. So use that equation again. CSS equal to R by CL. So what is the R? R is 280 and milligram per hour, and milligram per hour, and clearance is, I think, is 37 liter per hour. 37 liter per hour. So in that case, we calculate let's check this, 200 280 divided by 37, it is 7.57. so we have this 7.57. so now let's go back to that problem again. Let's go back to that problem again. You see a bolus dose immediately to achieve the a bolus dose in milligram to achieve the new steady state immediately. So he is asked, this question asks use infusion data. So steady state in infusion, steady state concentration was CSS was 2.04 milligram per liter, and then for bolus dose you have to use volume of distribution. Volume of distribution is volume of distribution V is equal to 118, but it doesn't make sense. Maybe I'm making some mistake. I'll make that correction later. I'll send that to you. Okay, that's all you have to do. If you have any question or suggestion, just let me know, but I will find out this what I'm making mistake here, so I'll find out and I'll post that part only. Thank you. I hope this helps. The problem was I have used wrong CSS, because if this is use infusion data here, in case of infusion data we have to use volume distribution 118, and CSS, our CSS is this one 5.8. so if you go back to your calculator, times 5.8, so 6.84. this was the should be 6 point, as it says, 6.84 684 milligram. I had to use, so you see that I am making mistakes, so you have to be very careful, because this question was related to this, but here it means use infusion data. In fact it is referring to use this volume distribution data. So I was using wrong CSS. CSS should be this one. So with this I'm done for assignment on IV infusion. I hope this helps. Thank you. If you have any suggestion, I know my handwriting is very bad, and also it is my computer and the pen makes it even worse. Thank you.